Okay, if I could have your attention, please, we shall get things started. Welcome to the final talk in our What Physicists Do series for this semester. I am very pleased to welcome our two speakers today, who are project/and/or research scientists, depending on which of them you'll be listening to, both coming to us from NASA's JPL facility. Both of them have such a wonderful and rich and successful academic background that it seemed redundant to introduce all of their achievements to you so far. So I thought I'd tell you the biggest impacts they've had on my life to this point. Jason introduced me to Panda Express, which has certainly changed my life in many ways. And Alina has introduced me to sushi. So I owe both of them greatly for their contributions to my time here. So I'm very pleased to have both of them along today. Let's give a very warm welcome to our speakers.
All right, so I think Tom has probably given you some idea of which of the two speakers is classier. All right, so I'm gonna go first, and I'm gonna talk about NASA's next astrophysics flagship mission, the Wide Field Infrared Survey Telescope. So first, I should probably tell you what I mean by next and what I mean by astrophysics flagship. So astrophysics flagship is a mission that NASA does. It's a big mission. And a flagship is a mission that NASA usually spends more than $1 billion on. And what I mean by next is in early 2019, NASA is going to launch the James Webb Space Telescope, which is really a replacement for the Hubble Space Telescope in many ways. It's much bigger than the Hubble Space Telescope. But we consider that almost done at NASA, something that's going to launch in 2019. So I'm looking beyond that. So next, beyond the James Webb Space Telescope, is hopefully the WFIRST telescope. And we're hoping to launch that in about 2025. So the WFIRST telescope was really born about 7 years ago, in 2010, in a process called the Decadal Survey. And I'm not going to tell you about the Decadal Survey because Alina's going to cover what a Decadal Survey in astronomy is. Thank you very much. But in 2010, a number of astronomers got together and they looked at a number of different mission concepts. One was JDEM, the Joint Dark Energy Mission, to study dark energy, and I'll tell you what that is. Another mission concept was the microlensing planet finder. This is a technique that we would use to find planets here in our galaxy, but outside of our solar system. And the other one was the Near-Infrared Sky Surveyor. It's a mission to survey big swaths of the sky in near-infrared or heat vision. And what this panel of astronomers found is that all three telescopes had kind of the same requirement. That is, they all needed a mirror about 1.5 meters across, and they all needed a big infrared focal plane. That is, lots of pixels to study the sky in the infrared. And by lots of pixels in 2010, I meant hundreds of millions of pixels. So that's a pretty impressive sized camera. But you know, everyone here probably has a camera in their pocket with some tens of megapixels or tens of millions of pixels. So this is only a few times or a 10 times bigger camera than what you have in your pocket, but a much more advanced camera. And so what this committee did is they said all three of these really important science goals would take about the same equipment. And so they said, we'll do it all together. We'll combine all of these into a single satellite. We'll call it WFIRST, the Wide Field Infrared Survey Telescope. And we'll try to do it for about the same cost as any one of these missions alone. So that's something we see a lot in NASA and science. We're told to do more with less money. And we figure out ways. So we started to study at NASA this WFIRST concept. And after about 2 years, we had a big hiccup in the process that was a good hiccup, and that we were given something called the Astrophysics Focused Telescope Asset. And so this is doesn't exactly roll off the tongue. NASA is not always known for its clever acronyms, but this AFTA is a repurposed 2.4 meter telescope from the National Reconnaissance Office, the NRO. So this is another government agency that builds space telescopes. They had this 2.4 meter space telescope sitting on the ground in a facility, and they decided they weren't going to use it. They weren't going to launch it into space. So they said to NASA, do you want this telescope? Now keep in mind that the WFIRST we were planning at the time had a mirror about half this diameter, so about a quarter of the area. So this new mirror is going to allow much more science, collect a lot more photons. So NASA did take control of this telescope, and I'm showing you actually a couple pictures of the WFIRST telescope, which is in a facility in New York sitting on the ground. We're repurposing this telescope that we're pretty sure was made to look down. We're going to point it up. And this new telescope, because of the bigger mirror, is going to allow us to include an instrument called a coronagraph to image exoplanets. And I'll tell you what a coronagraph does. And of course, this wasn't part of the original WFIRST, because the original WFIRST, as we envisioned early in this decade, didn't have a mirror big enough to make use of this coronagraph instrument. So this is really, adding this is enabled by this 2.4 meter mirror. So we have a number of science goals that reach back to the 3 missions that went into WFIRST. The first is to characterize the history of cosmic acceleration and structure growth. What that really means is we want to study dark matter and dark energy. I'm going to tell you a little bit about what those are. We want to understand how planetary systems form and evolve. That is, how do planets and solar systems form? How do they evolve over time? And we're going to do this with 2 different techniques. One to look for lots and lots of planets, and another technique with the coronagraph to look very carefully at a few planetary systems and look at the planets themselves. We'll study also the debris disks. Those are the disks of stuff that eventually collapse into forming planets. We want to maintain a robust guest observer program. So a guest observer program is when anyone in the worldwide astronomy community can put a proposal into NASA and earn time on the telescope. So some of the WFIRST time is going to be set aside for anyone to propose what they want to see with WFIRST. So I'm going to start talking a little bit about the WFIRST science. And I'll mention, again, the science that I talked about previously. It's divided up into, this is really the dark energy science. We're going to study dark energy with 3 techniques. One is called gravitational lensing. This is the bending of light from distant galaxies by dark matter. Another is supernova. That's exploding stars. And the third one is baryon acoustic oscillations. Again, we don't always have the cleverest names for things, but this is really a fancy way of saying the clustering of galaxies, how close galaxies are to each other. We're also going to do microlensing. This is a technique where we look at stars and we wait for those stars to blink, and in that blink of the star, we can actually see evidence for a planet around that star. And then there's the coronagraph, which is how we're going to actually image and take spectra of planets, and the guest observer program. And one of the reasons I particularly like this graphic is that in our idea of what the WFIRST mission will look like starting in the mid-2020s, the size of these boxes here is about roughly the amount of time we would spend on each of these different science goals. So that's how we're going to divide up the science and observing time of WFIRST. And how are we going to do all this great science? Well, here I'm showing you a picture of the Andromeda galaxy. And I want to make the video play, but that's not working. There's a video here. So there was a couple years ago, there was a program to look at the Andromeda galaxy with the Hubble Space Telescope. This is the nearest galaxy to ours. So each of these squares is a picture we took with the Hubble Space Telescope. So it took 432 times pointing the Hubble telescope to look at the Andromeda galaxy. We would be able to do that with 2 pointings with WFIRST. So the WFIRST field of view, the WFIRST camera, is more than 100 times as big as the Hubble camera. So we have a telescope that's exactly the same size as Hubble, but it'll be able to take pictures of hundreds of times more sky than Hubble because of advances in these detectors. And that will be enabled by this, what we call a wide field instrument. So this wide field channel has a number of pixels that's quite large. It has 18 detectors in here, each with 4K by 4K pixels. And then we'll have also inside that instrument, we'll have what's called an integral field channel spectrograph with a smaller field of view. So the optical channel here, this wide field channel, that'll take pictures like what you would see from your phone camera or what you see in astronomy textbooks and hopefully things like on the front page of the New York Times. This IFC, this integral field channel spectrograph, what that's going to do is it's going to divide out the light from a star or a galaxy into its component parts, into its spectra, into a spectra, and we'll be able to look at that spectrum We'll be able to tell what are the components of the galaxy, and one of the other things we'll be able to tell from that spectrum is how far away that galaxy is. And that's going to be a key part of understanding the history of the universe. So my background is in cosmology, the study of the universe as a whole. So I often start a talk on cosmology with this pie chart. And this pie chart represents the components of the universe. And you'll see that this is a pie chart that is not divided into very even pieces. So if at Thanksgiving the pie was divided like this, you'd have a lot of unhappy people and maybe one happy person. But the interesting thing about this pie chart is all the normal matter, the stuff that makes up us, galaxies, everything we see in the universe, is about 5% of the universe. And there's most of that is in gas, a little bit's in stars and neutrinos. And one of the things that doesn't even register on here, but something I'm going to talk about and then Alina's going to talk about, are planets. So planets are such a small part of the universe that they don't even register on this pie chart. So for about a century, we've known that there's this normal matter, but there's a lot more dark matter out there. And this is matter that we know it's out there because of its gravitational interaction. We can test and see that the matter is out there because of gravity, but we actually can't see it directly. For about 20 years now, in fact, we're coming up next year on the 20-year anniversary of knowing that that's even dwarfed by this dark energy. There's more dark energy in the world than dark matter. And dark energy makes up about 70% of the universe. And dark energy is the name we give to whatever's causing the accelerating expansion of the universe. That is, for about 20 years now, we've known that the universe is not just expanding, but that expansion is accelerating. It's expanding faster and faster. So with dark energy, okay, this is going a little bit crazy. There are two top-level questions. Is this cosmic acceleration caused by a new energy component in the universe? And keep in mind, if it is, that new energy component in the universe is the biggest chunk of what's out there in the universe, or is it caused down a breakdown of general relativity, our understanding of gravity on cosmological scales? Either one of these explanations is huge because it requires new physics on top of the physics that we've known about for many hundreds of years. So either one of these explanations for what's causing this accelerated expansion is likely going to win somebody a Nobel Prize and really change our understanding of the entire universe. We also want to know, is the cause of this new this new energy component, is it constant in space and time, or is it changing, evolving over the history of the universe? Does it look different in the past than it does now? We're going to use three techniques to do this with W first. The first is this gravitational lensing technique, where the light from distant galaxies is bent by the foreground dark matter. So you see these galaxies as we have a dark matter structure that would be going across this picture. We don't see the dark matter, but we see the bending of the light in the distant galaxies. And in that way, we can study this dark matter. And by studying the dark matter over different times in the past, we can recreate the dark matter like this. And the clustering of that dark matter over time is given by an interplay between the attractive force of gravity and the repulsive force of this dark energy. So by using this gravitational lensing technique, we're going to be able to learn about the dark matter and dark energy. So we'll also use galaxy clustering, and that is, we'll look at the positions of galaxies on the sky. And again, those positions of galaxies are going to be given by an interplay between gravity wanting to pull the galaxies together and dark energy wanting to push them apart. And finally, we're going to use supernova, that is exploding stars. And a particular kind of supernova that we're going to use with W first is when there's one star orbiting another. The smaller star that's actually more dense is pulling stuff off of the bigger star, and when it gets to some certain level, it becomes unstable. And when it becomes unstable, it explodes. And with that explosion always pretty much looks the same. And so we use it as what we call a standard candle. And so the further away this standard candle is, the dimmer it will be. And we can use these standard candles to measure the expansion of the universe over cosmic time. So there's really these three techniques that we're going to use with W first to study the dark energy. And there's two consequences of dark energy that we're going to look at. We're going to look at the expansion history of the universe, which we also sometimes call the geometry of the universe. That is, how fast did the universe expand? And we're going to look at the growth of structures, these structures that are mostly dark matter. How do they grow over time? Again, that's attractive gravity competing with repulsive dark energy. And if Einstein's theory of relativity is wrong, so we could have to modify gravity theory. And it's only by looking at both of these that we're going to be able to distinguish between possible modifications to gravity and theories of dark energy. And so what I'm showing here is, this is a map of the cosmic microwave background radiation. This is the universe as it appeared at about 300,000 years after the Big Bang. And you see hot and cold spots, red and blue here. And those hot spots correspond to overdense regions in the universe. And those overdense regions grow through gravitational instability. That is, if there's more stuff, there's more gravity, so it's pulling stuff in. And those grow to be the galaxies we see in the universe today. So this is a picture taken by the Hubble Space Telescope. And each of the little splotches of light there is a galaxy, much like our own, with hundreds of billions of stars in it. And so over the history of the universe, these hot and cold spots have grown into the galaxies and structures of galaxies we see today. But keep in mind, we're really only seeing the tip of the iceberg there. That is, those galaxies, what we actually see is only about 1/6 of the actual mass that's there. Most of it's dark matter. Just like if you have an iceberg, you only see the tip of the iceberg, and most of it's hidden beneath the surface of the ocean. So most of the universe still remains hidden even when we look at these galaxies. So now I'm going to move on, and I'm going to talk about microlensing. So microlensing is a technique, again through this gravitational lensing, that's going to allow us to find planets. So what we'll do is we'll study many, many stars in the center of the galaxy, and we'll observe them over time. And if those stars happen to have one star go in front of another, that's what you're seeing here. This star with a planet is going to pass in front of this star. And what we'll be looking at when those stars pass in front of each other is this background star is going to be magnified. And this is what we see. We see the brightness of the background star looks like this. It goes up and then goes back down as the stars pass in front of each other. And you'll see that there's this extra blip. That extra blip of magnification is from the planet. And you're seeing it here again. And the time scale for this is several days. So as the star passes in front of another star, we see this brightening of the star over several days. But there's only several minutes or hours that the planet actually does this magnification. And by looking at many, many stars, many millions of stars with W first over many months, we'll be able to see actually evidence for about 3,000 planets. So we'll find about 3,000 new planets. And this is going to be really exciting because we actually have a spacecraft that NASA's been flying for a number of years called Kepler, and it's found many, many planets, thousands and thousands of planets. These blue planets are the ones, these red planets are the ones found by Kepler. And what I'm showing here, this is the planet mass in Earth's mass, and the semi-major axis, that is the distance from the sun in astronomical units. So Earth is here, of course, at 1 Earth mass and 1 Earth distance from the sun. And so Kepler finds these planets over here that are close to the star, and W first will find planets that are further from the star. So it's really, as I said, completing a census. So when you combine it with the Kepler data and the W first data, we'll be able to look at the whole range of planets and planet formation that we see in our galaxy. And there's actually, the black points here are planets we found using other techniques. So most of the planets we've found so far are with Kepler, and in 10 or so years, we'll have at least that many more that we've found with W first. But really, these planets are going to be very far away, and they're not going to be ones that we can sort of follow up and learn about very well. So to do that, we'd want to use a coronagraph. And so I'm going to show you a video here of how a coronagraph works. So this is, of course, an artist's recreation of how a coronagraph would work. But we have this planet orbiting this star, and the star is 1 million to 10 billion times as bright as the planet. And so what we need to do is we need to block out the light from the star in order to see the planet. And so what a coronagraph will do is we'll have an optical element inside the telescope that we'll put in front of the star to allow us to see the light from the planet. Now this seems pretty simple. We just have to figure out a way to put this disk right in the path of the telescope in a way that will block out the central star but leave the planet as something we can observe. But coronagraphy is pretty challenging. Now I'm going to show you a video with sound that one of my colleagues at JPL has done. It's about 2 minutes, and this is going to tell you why coronagraphy is challenging and why WFIRST, one of the things we're trying to do is build a new coronagraph that will allow this.
A distant star is orbited by 2 planets. One looks similar to the Earth, the other is a gas giant. When viewed from a distance, the 2 planets disappear into the glare of their sun. How could we ever find these planets all the way from the Earth? By using a space telescope with a coronagraph to separate starlight from planet light. As the star's light passes through the telescope's large mirrors, it picks up small distortions. Diffraction adds concentric rings to the image we see. To reveal the planets, first a coronagraph uses a mask to block much of the star's light and redirect the remaining light to the outer edges. A washer-shaped device can now block most of the rest of the star's light. Because the planet's light comes in at an angle, it misses the mask and passes through the center of the washer. But when we turn up the image signal by collecting more light, we can see that the planets are still hidden under blobs of leftover starlight. To remove these blobs, the coronagraph has a special deformable mirror that can change shape by using hundreds of tiny pistons. This can correct distortions in the light beam. As the mirror deforms, the blobs of light as seen in the monitor slowly begin disappearing, finally revealing the brighter of the 2 planets. Afterwards, the fainter planet also comes into view. We can now see objects more than 1 billion times fainter than the star. And if the light from these planets is passed through a prism, we can spread it out into rainbows of color. But some colors are missing. They were absorbed by gases in each planet's atmosphere, giving us important clues about their composition. The search for life in the universe has taken a new step forward.
So making a coronagraph like this work is really challenging technically, and that's one of the things that we're working on with for WFIRST. In fact, that's what we're building at JPL, where I work. And you saw these deformable mirrors. They're these very tiny mirrors, maybe about the size of your thumbnail, but they've got many hundreds of pistons that change the shape of the mirror. So that's just one of the pieces of technology that we're developing to do this. And as you heard at the end of the video, one of the holy grails, one of the things we're looking for is possible signs of life on these planets. And we measure the performance of coronagraphs in powers of 10, really. That is, the powers of 10 are the contrast between the planet and the star. So the best coronagraphs that we have now reach a contrast ratio of about 10 to the 5 or 10 to the 6. That is, you can look at planets that are about 10,000 or 100,000, or 100,000 or a million times fainter than the star. But WFIRST requirements are for 10 to the 9. So 1,000 times better than any coronagraph we've ever built. And we've already demonstrated much better than 10 to the 8th in the lab. We have 2 different types of coronagraph that we're working with for WFIRST at JPL to test which one's better in space. But what we really need to look for an exo-Earth, that is a planet the size of Earth, about the distance Earth is from the sun, we need a coronagraph even 10 times better than WFIRST. And there are a couple options that NASA's looking into, including a mission called HABEX, which is what Alina's going to talk about in just a couple minutes. And so really the holy grail for coronagraphy is being able to look at and take a spectrum of Earth. And so where we are now is these coronagraphs. And this is the contrast ratio I was talking about. And this is the separation of the star from the planet. And Earth is down about here. So these are the coronagraphs that are either in place now or will be in place in the next few years. They can do that. What we're going to do with WFIRST is down here. So we're going to take a big leap forward by a factor of about 1,000 in capability with WFIRST. And that's going to leave us about a factor of 10 less than what we need to image Earth. And as I said, Alina is going to talk about a possibility for doing that. So I'm going to skip this, and I'm just going to tell you about some opportunities that are coming up with WFIRST. And when I say opportunities, I'm specifically thinking about opportunities for people here. So WFIRST will have about 25% of time for guest observers in the first 5 years of its mission. But we actually anticipate that WFIRST will last longer than the planned 5 years, could last up to 10 or more years. And after that first 5 years, we'll have 100% of the time given over to guest observers. And since this mission is going to launch in 2025, we expect this big guest observer program to start in about 2030. So anyone here as an undergrad working in astronomy, you're going to be well into your astronomy career in 2030. And so I'm reaching out and saying, you should start thinking about what you can do with WFIRST. There will also be guest investigator calls. That is, as we do these surveys for find planets and look at dark energy, other people will think of other ways to use that data, and NASA is going to make money available to investigators to look at that data in different ways. And all the science teams for WFIRST will be competed in 2021. That is the prime survey science. And we're also going to consider in 2020 a decadal survey, which Alina will talk about. We'll consider a star shade, which is another way of getting rid of the light from the star so that we can see the planet. And it's something that Alina is going to cover. So I'm going to stop here.